we're going to talk about Newton's third law and momentum. Before we get started thinking about exactly what those terms mean and defining them, I want you to think about the following situation. So why do firemen's hoses have large handles at the nozzle? If they didn't have a large handle, what would happen? We've got this force of the water coming out of the hose, right? And otherwise it'd be hard to control. Next question, why would it be wise to secure your boat before you jump onto the dock rather than just after? Well, what would happen if you didn't secure your boat before you jumped off? If you have any experience with this, the boat would slide the other direction, right? If you jump forward, the boat would slide backwards in the water your way. So today we'll be able to answer why the boat goes backwards. And then the last question, if you fire a gun, why should you brace yourself? And that answer has to do the same thing. The bullet would move forward, and so the gun's going to go backwards. So you need to brace yourself for that. We'll start off talking today about Newton's third law. Newton's third law says that for every action force, there is an equal and opposite reaction force. For every action force, there is an equal and opposite reaction force. So what that means is that forces are always going to occur in pairs, where if object A applies a force to object B, then object B will apply an equal force in the opposite direction to object A. So that means if I push on the wall is pushing back on me. A little counterintuitive, but that's what Newton's third law says, and that's what happens. Now, one thing I want to note is sometimes people get mixed up and they think that sometimes say Newton's law is for every action there's an equal and opposite reaction. That's true, but we're talking about forces. So keep in mind this is not a cause and effect. It's not that you did something and it caused something else to happen. It's that you applied a force and you felt a force back on you. Examples of Newton's third law. So one example is when you sit in a chair. When you're sitting in a chair, your body exerts a downward force on the chair, and we see that in the picture here. And the chair exerts an upward force on your body. So you apply a force down, and the chair applies a force up. They're equal and opposite directions. Another example, if we have here's another picture of it, we have your force on the chair, or your weight pushing down, and the reaction force then is the chair applying a force on your body. Another example would be the baseball applies a force to the bat, to the left, we see here, that's the action force, and then the bat applies a force to the ball to the right, that's the reaction. So that's equal and opposite. And that reason is why if you hit a ball, you feel, right? You feel it if you hit a ball that's going really fast, you feel it in your hands. And the reason is because you applied to the force to the ball, but the ball's going to apply a force back on you. And that's why you feel it and it might sting a little. Another example, fish moving through the water uses its fins to apply a force to the water. And then the water reacts by applying a force to the fish, propelling the fish through the water. And that size of the force on the water is equal to the size of the force on the fish. And the directions are equal and opposite. So on the water, it'd be backwards, in the opposite direction of the force on the fish, which is forwards. And we can see that with this video. So if you open the PowerPoint, you can get the link to the video. Another example here, this is kind of a funny example, looking at action-reaction force pairs. So again, open the PowerPoint and you can look at this video and see what's so funny about it. So if we look at this situation, so looking at this example, what is the action force here? Well, we have this astronaut coming in from the left is applying a force on the other astronaut. So the object that force is applied to is this other astronaut that was just standing there. The reaction force in this example is that this astronaut is going to be pushing back on the first astronaut. And so it's applied, this first astronaut applies a force to the second astronaut, and then the second astronaut applies a force to the first astronaut. So the objects change. The forces are opposite direction, but the objects that they're acting on changes from acting on the second astronaut to acting on the first astronaut. Another example of Newton's third law, reaction of a rocket. Fuels are burned in the engine, producing hot gases. Hot gases push against the inside tube of the rocket and escape out the bottom. Gases move downward, and so they're going to apply a force downward, and so then that will apply an equal and opposite force in the air in the opposite direction. That's why the rocket goes up. And you can see that if you click on this page. So momentum is also related to Newton's laws. Momentum is the product of mass and velocity. Now, momentum starts with an M, and it'd be great if we could call it M and use that M symbol, but we're already using M for mass. So when we're talking about momentum, we use a P. So our equation, momentum, is the product of mass and velocity. We read it as P equals M times V. We use a P for momentum. One thing to note, when two objects collide, momentum is conserved. So what that means is momentum stays the same. It's not lost, it's just transferred. And that kind of applies to some of our situations in the beginning. If you remember back to why you should tie your boat up, if we think about in the beginning, our momentum was 0, right? Because our velocity was 0. And in order for momentum to be conserved, this is kind of like a reverse collision. You separating from the boat. If you go off the boat one direction, in order for net momentum to be 0, the boat has to move off in the other direction. So that's something to think about and why that happens with the boat. Big idea here, momentum is mass times velocity. And when two objects collide, momentum is conserved. So whatever you had at the beginning is going to be the same as what you have at the end. Here's our triangle for momentum. So the units for momentum, because it's mass times velocity, is going to be kilograms, meters per second. And there's no shorthand way to write it. It's kgm per s. And then for our triangle, we have P on top and then m, v. I want you guys to think about this, because we'll later do a lab on it. Which has more momentum? A tennis ball moving fast, or a tennis ball moving slowly, or a bowling ball moving fast? Think about it, think about it. Which one has more momentum? Did you think about it? Are you still thinking? Well, a bowling ball, let's look at the equation for momentum. So momentum is mass times velocity. So a tennis ball has a pretty small mass, but if it's moving fast, it has a big velocity, which means it has more momentum than a tennis ball moving slowly, because that has a small velocity. Now a bowling ball has a big mass, and if it's moving fast, it has a big velocity. That means it would have the biggest momentum. So a bowling ball moving fast has the biggest momentum. And so I want you to think about that, and we'll later look at this with a demonstration. Well, that's all for today. So big ideas here. Newton's third law says that for every action force, there's an equal and opposite reaction force. Or in other words, if I'm applying a force to an object, the object is applying an equal and opposite force back on me. Then we also talked about momentum, which is mass times velocity. So the more mass, or the faster something's going, the more velocity or the more momentum it has. That's it for this video.